Good afternoon, everyone. Am I audible?
Yes, ma'am.
Yes, ma'am.
Hello, I'm Sushmita.
Hello, ma'am.
I'm one of the course instructors of Maths 2. So you've already had your first live session. How did it go?
Good, madam. Good.
So you got your doubts cleared there, right? Yes?
Yes, ma'am. Yes.
Yes, ma'am.
Okay. So maybe in today's session, we'll revise some topics and then get the corresponding doubts cleared for those topics alone. Is that okay?
Yeah. Yes.
Yeah, ma'am.
Yes, ma'am.
Yeah. So we usually have this kind of an idea where in the 3 live sessions, we'll try to split the topics of a week in 2 live sessions and discuss the topics as well. Just recall kind of, and one session may be completely dedicated only to doubts. So this is the general plan, but in case you're not okay with it, we can customize it according to your needs. Okay, so maybe we will start off with discussing the topics today, and you can stop me whenever you have a doubt, and we will like consider the doubts from activity questions or anything, maybe at the end of each topic.
Ma'am, if you are you open for a session?
Yes, please, sure. Go ahead.
Actually, last Maths 1, Mr. Vicky and Shrikant, they used to brush up the full week content, and then at least once in that 3 days, once they used to summarize everything, and then they would start.
Yeah, that's what we are going to do.
Okay.
A little more than summarize, maybe here.
Oh.
Yeah. Okay. Is my screen visible?
Yes.
Yeah,
It is
ma'am.
visible.
Okay. Can you see that I'm writing something?
Yeah, we can see that.
Yes, okay. Fine. Okay, so week 1, it has some very basic contents that is needed throughout the course. So we'll start off straight away. What is a vector? You've all seen a lot of vectors. So what is a vector in general?
A line with an arrow.
List
Something
of
which has
numbers, ma'am.
magnitude and direction.
Yeah, so if you take the 2-dimensional plane, it's something which has a magnitude and a direction, right? So we represent it like this. We represent it by an arrow. It starts at the origin and ends at the vector. Whatever is the vector, that is our vector. Okay. So if it is in the two, yeah.
I mean, I think in one of the lectures, or I think in the notes or question somewhere, it was written that we should not think of vectors like that, and that we
Yeah.
now we only think as like numbers only, something.
Yes. I'm coming to that.
Okay.
Yeah. So this is how we have seen vectors and all that. So in our course, for us, vectors just means that it's this coordinate or the pair that we have, a comma b. That is a vector for us. So yes, so a vector, you draw it on a 2D plane and all that, and it has an x coordinate and it has a y coordinate. So for us, the vector is now just that point in R2 with an x coordinate and a y coordinate. So it's a 2-dimensional vector if it has 2 components. It's a 3-dimensional vector if it has 3 components and all that. So for us in our course, by a vector, we just mean an element in R2 if it's a 2-dimensional vector. If it's a 3-dimensional vector, it's a point in R3, etc. So vectors.
I want to ask one short question. Would you be sharing this PDF in the end?
Yes, once the live session is over, we will upload it in the portal. It will be available in the supplementary content.
Thank you, ma'am.
Yeah. Okay. So vectors in R2 are represented by ordered pairs because it has an x component and a y component. So it has, every vector has 2 components, where the first component is the x component and the second one is the y component. And if you have two vectors, you know how to add them. How do we add two vectors?
Coordinate wise?
Yeah, it's component wise. So you add the first component of the first vector with the first component of the second vector. Similarly, the second component of the first vector with the second component of the second vector. That's how you add two vectors. And scalar multiplication. What do you mean by scalar multiplication?
Multiplying with the constant.
Yeah, you multiply a vector with a constant, a scalar. So a scalar for us is a real number. So throughout the course, for us, scalars are real numbers. So when you multiply a vector with a scalar, that's called scalar multiplication. So scalar multiplication is again defined component wise. So when you multiply a vector with a scalar, what you do is multiply each component of the vector with the same scalar. So that's what you do in scalar multiplication. So what happens when you multiply a vector with a scalar? Suppose I have a point A comma B. What happens when you multiply this point with a scalar? Geometrically.
It moves along the same line.
Or it will reverse.
The slope doesn't change.
Negative.
Yeah, it's going to be on this line. It's either going to elongate or it's going to shrink based on what the scalar is, or the direction gets changed or anything. So when you multiply a vector with a scalar, it's going to lie on this same straight line which passes through the origin. So these are two important operations which will be used later on in the course, where when we study vector spaces and all that. So that is why we are considering only these two operations here. So once you know to add two vectors, you also know to subtract two vectors, right?
Yes.
Yes. Because V1 minus V2 is nothing but V1 plus minus V2, where minus V2 can be written as minus 1 times V. So now we know how to add two vectors, and we also know how to do scalar multiplication on vectors. So we know how to subtract vectors. But there's no concept of multiplication of vectors, right?
Yes.
There are various products which can be defined, but
Hello, madam.
Yes.
Hello, madam. Point and vector are same. I think points and vector two are different thing or two are same.
No,
Points.
See, what you study. Okay, you mean if this point A comma B and the vector A comma B are the same, is it?
Okay, okay. Yes, ma'am.
Is that your question?
Yes, madam.
Yeah, so the elements of R2 are just called vectors. That's it. That's what. We are all heading to one general concept of a vector space. So that is what is the ultimate goal. Like we will be studying vector spaces from week 3 onwards. So in vector spaces, the elements of a vector space are called vectors. That's it. So in the vectors that we have here are not the vectors that we studied in physics, but they are elements of R2. As of now, we can think of them as elements of R2 or R3, whatever, based on the number of components. They are just points. Yes, you're right. Okay. Then, yeah, shall we quickly do this problem? We have two vectors. V1 is 2 comma minus 4 and V2 is minus 1 comma 2. These are elements in R2, right? Because they have two components. Yes?
Yes, ma'am.
Yeah. So how do we add these two vectors? Or yeah, there are some options given here. What is 2 times V2?
2 times
Minus
V2
2
is
comma
minus
2.
2 comma 4.
2,4.
Yeah. 2 times V2 is, how you multiply is 2 times minus 1 comma 2 times 2. So that's going to be minus 2 comma 4.
4.
And then half V1, you do the same.
1 comma minus 2.
1 minus 2.
minus.
Yes. And how will you add V1 and 2V2?
0, 0.
2 minus 1.
Yeah.
Minus 1.
2V2 is here and then V1 is here. So when you add those two component wise, you'll get 0, 0. 2V1 plus V2.
Incorrect option.
This is
Yeah.
incorrect.
3 comma minus
2v1 is 4 comma
4 comma minus 8
minus
plus minus 1 comma.
Yeah,
Minus
v2
1.
is this. So 2v1 plus v2 is
3
comma minus
3
minus 6.
yeah. So this is not the right option. Okay. So this is basics, and you all know about this. And the same thing carries forward to R3 as well, where the vectors have 3 components: the x component, y component, and z component. So again, you add 2 vectors in R3 coordinate wise, and you do scalar multiplication coordinate wise. Okay, so in this, yeah, there's a problem here. We have 3 vectors. Can you tell me where the vector 1, 0, 0 lies on the
x-axis?
X-axis.
On the x-axis.
X-axis.
Yeah. So the
coordinate.
vector 1, 0, 0 lies on the x-axis, and the vector v2 lies on the
y-axis.
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 and v3 lies on the z-axis.
Z-axis.
Okay. And let these be 3 vectors, and a, b, c be 3 real numbers. Then which of the following are true? Okay. What is the vector a, b, c in terms of these 3 vectors?
Correct.
First one is correct.
Yeah. If you have any point in R3, what you do is you just express it in terms of these 3 basic vectors that we have. A times 1, 0, 0 plus b times 0, 1, 0 plus c times 0, 0, 1. That's because when you do all these scalar multiplication and then do the vector addition, you're going to end up with this vector. What about option 2?
Is incorrect.
Incorrect.
Yeah. Option 3 is
Incorrect.
Incorrect.
option 4.
Correct.
Correct.
Yeah. Option 4 is nothing but put b is equal to 0 in option 2. That's it. Okay. So yeah, I guess we've covered the basics of vectors. Do you have any doubts in this?
No, ma'am.
Okay. So
Ma'am, how come the option of 4 is correct? Can you please explain? How come V is 0?
No.
V2 0?
A0C. No? So that's
A0C. So it can be written as A times 1, 0, 0 plus 0 times 0, 1, 0 plus C times 0, 0, 1.
0, 0, 1.
Okay, got it.
You take the right hand side and simplify to get the left hand side.
Yeah. Thank you.
Ma'am, one clarification. The term scalar is just a terminology for constant, or it has some special meaning?
No, there's one concept called as field, and the elements in the field are called scalars. So for us, the field is R, set of real numbers. So for us, real numbers are scalars.
means we can safely consider that as a Peters constant.
Yeah, scalars are real numbers. That's
real
it.
numbers.
And also there's something that won't change, right?
Change. That's what means. There is no direction.
Yeah.
Hello, madam.
Yes.
Madam, actually, vectors have direction and magnitude. But why we are using this particular term in matrix? Can you say that matrix also have direction and magnitude?
No. See, I had mentioned earlier that we are going to study the general topic of what is called as a vector space, and the elements of a vector space are called vectors. So that is why all these are vectors for us.
Okay.
You will, from week 3, you will understand that all these are vector spaces, and that's why its elements, that is these vectors like this, are actually called vectors.
Okay, elements of vector are called matrix.
Yeah, elements of a vector space are called vectors. That's
okay.
Ma'am, and how do we represent it in a diagram like the additions? Can you please explain once?
So you know the parallelogram law of addition? if
Ma'am,
you
I'm
have
not
to.
clear with that part
Sum
actually.
of the two sides is equal to diagonal.
Yeah. So if you have two vectors, what you do to find out the sum of the vectors is you complete this parallelogram. And then you take the diagonal. This is going to be the sum of the two vectors. If this is A and this is B, this is going to be A plus B.
Excuse me, ma'am. For
Yes.
this course particular, are we going to study only parallelogram law, or we are going to study triangle law also?
Triangle law also says something similar, right? Yeah. There
Yes, ma'am.
you
Both
have
are
B
same
like this.
exactly.
Yeah. Yeah. No, we are not studying parallelogram law or triangle law or anything in this course, because for us vectors are not what we studied in physics. They are just points in R2 or R3, and we know how to add points in R2 or
Yes,
R3.
ma'am.
Yeah.
And one more, just a follow-up question. We tell that R2, R3. So we have only three spaces. Single means R1, R2, R3. Yes.
You can think about Rn in general, where every vector has n components.
No,
But we are
have
mostly
only X, Y, and Z plane. Only three planes are possible.
No. Fourth dimension, add time to it, add something else, you get a 5-dimensional something.
Oh.
We are not able to see it, that's it. We can see only up to R3.
But in a drawing and all, we will restrict only to three dimensions. Right?
Yeah, that's because we can see only up to R3, right? We cannot see a fourth dimension, right? For us, where we live in is 3-dimensional, right?
Yeah. So we will be restricting. Are we restricting to 3-dimension, or we will be means Rn what we got?
In most of the cases, we will try to keep it up to R3, but we will be studying in general about Rn.
Okay,
Yeah.
there is a possibility, but mostly it will be R3.
Yeah, yeah.
Okay.
Ma'am, when in physics we add vectors, so angle between vectors is also matters. But here, what we will do is just adding 2 points. We will not have to think about the angles, right?
Yeah, that's
Between
because,
vectors.
as I told you, the vectors here for us are just elements of a vector space. And when you study vector space, you will understand that there are two operations associated to a vector space, that is addition and scalar multiplication. So that is all what we want.
So there is no vector multiplication like in vector space.
No, there is no multiplication. There is only addition and scalar multiplication. So these are the only two operations for a vector space.
Okay.
Yeah, about the angle and all that, yeah, this concept of dot product and all that will come later on. There's something more, like more than dot product. There's something called as inner product. So when we study that, we'll get into the angle thing also. But again, a vector space is a general concept. It's an abstract concept. It's just that R2, R3 and all are examples of vector spaces. So we can associate all this to the general concepts that we study. This vector space is an abstract structure.
Okay, ma'am. Got it.
Yeah. Okay. Then matrices. Matrices is something which all of you already know. It's just an array of numbers arranged in rows and columns. So what is the order of a matrix? So I have a matrix.
Number of rows and number of columns.
Yeah. The order of a matrix is the number of rows cross the number of columns. So you first write the rows and then write the columns. So you can have rectangular matrices where the number of rows is not equal to the number of columns. Or you can have square matrices where the number of rows and number of columns are the same.
Equal.
Like, yeah, for example, this matrix, the matrix A that is given here, this is a square matrix because the number of rows is equal to the number of columns. Here we have a 3 cross 3 matrix, right?
Yes,
hello, ma'am.
Yes.
Is there any connection between vector and matrix?
Yeah, I'll get to that.
Okay.
You can see each of the column of a matrix as a vector, right?
Yes, ma'am.
or each row as a vector.
Yes, yes, ma'am.
Yeah.
Yes, ma'am.
So a matrix is nothing but putting vectors together. Here you're putting 3 vectors in R3 together to form a matrix. You can view it like that, or else 3 vectors in R3 like this as rows.
Like the example which was given for these items and the stock and the buyer ABC. We can visualize that, right?
Yeah.
Yes, ma'am.
Yeah.
Ma'am, this
back to the previous
PDF,
screen?
this
Okay,
you are referring, where would it be available?
After the session is over, we'll upload it and it will be on the supplementary contents tab.
Okay, ma'am.
Can you go back to the previous page? No?
Yeah, sure.
Now, can you represent this as matrix like B1 equals 100? So if you provide a square bracket, B1 100, B2. Okay. So B1 you are putting as a column. Okay. I made it as a row. Okay.
You can do that as well.
Okay.
Even if you do it as a row, it is going to be the same, right?
Correct. Yeah. Anyway. Correct. So this is the connection. What you are talking in the second page.
Yeah. So what I'm telling is, if you have a matrix, you can think of each row of a matrix or each column of a matrix as a vector.
That makes sense.
Yeah.
Okay.
So, yeah, when can we add 2 matrices? Can I add a matrix with 2 rows and 3 columns, with 3 rows and 2 columns?
No, the
No,
order
no, ma'am.
of the
No.
matrix should
Order
be the
should
same.
be same.
Yeah, the order should be the same,
We can
because I know to add 2
order.
vectors, I have to do it component wise.
Yes, ma'am.
So even if I have 2 matrices, if I want to view them as vectors, they should have the same number of components and same number of vectors and all that. So you can add 2 matrices only if they are of the same order. Here both are 3 cross 3, so I can add them. Again, because I know how to add vectors, I know how to add matrices. I have to add them component wise. Okay, and what will scalar multiplication of a matrix be? What will
We will
alpha
multiply
times A be?
each element of matrix will get multiplied by alpha.
By a constant.
Yeah. So each entry of the matrix will get multiplied by the constant, not just a row or just a column or anything. Each entry will get multiplied by the constant alpha. Okay. When it comes to matrices, we know that matrix multiplication is well defined. So when can we multiply 2 matrices?
The number of columns in the
columns
first
of
matrix equals to the number of rows in the second matrix.
The number of columns of the first matrix should be
is
equal to the number of columns of the second matrix. Yeah. So, yeah, before defining what actually product is, let's see what happens when I multiply a row vector with a column vector. When do I call a vector as a row vector? Or row matrix?
Only one row is there.
Yeah. It's a matrix with only one row. Then it is a row matrix. The column matrix if it has just one column. Column matrix or column vector.
One small doubt actually.
Yeah.
See, whenever we define matrix, first we always come with the row first. Row cross column. But when it comes to multiplication, why we take column first and then row? Why we are comparing column and row? Any logic?
No.
You don't take columns first. It's just that you need to.
I understood that why we are comparing column with row. First we are comparing column. We are taking column. 3 into 3. So then it makes sense. So, but 3 is the column and 3 in the second matrix is row. So why suddenly we are jumping the sequence?
Yeah, so that's what. It'll be clear because, if I have a row matrix and a column matrix, so this is going to be like 1 cross 3 and this is going to be 3 cross 1. Now, the definition of how the product is defined, how I can multiply this vector with this vector is by multiplying each of the corresponding components and then adding their products. So A into D plus B into E plus C into F. This is how the product is defined. So this is the definition. This is how the product is defined. AD plus PE plus CF. So I'm going to end up with a 1 cross 1 matrix or just a number, right? Yeah. So this is how the product of a row matrix with a column matrix is defined. So once this is defined, I can talk about product of two matrices, right?
Ma'am, one small doubt here.
Yeah.
Ma'am, what is the practical application of this multiplication of these two matrices? Let us say if it is row matrix or column matrix, what is the practical application of this phenomenon, ma'am?
No, this forms the basis, right? You talk so much about matrices, you talk about inverse of a matrix and all that. There are a lot of things that you talk about matrices. Without matrix multiplication, none of that would be possible, right? So this is like the definition.
This is the algebra of matrix. Plus, minus, into. That is what we're doing.
Also for the system of linear equations to solve.
Yes.
Yeah.
See, if you want to do some operations like plus, minus, into, you should know how the rules work, right? That is what.
Yeah, this is like the
This
tables
is the
that
rule
we
for,
study in school.
Yeah.
And I believe there might be some application in Python and all also, so this might form the basis for programming also, if I'm not wrong.
Yeah, matrices
there
are
is.
nice because you store data in stacks, right? So
yeah,
I'm not very, I don't know anything about it, but with the little that I know that the data, it gets stored like this, right?
Yeah.
Each
Table
bit gets stored and then, right?
Yes, ma'am.
Yeah.
We have
So,
seen in computational thinking.
Yeah, CT are doing like this.
In Python also they told about the matrix multiplication using.
For the depth first search also we implemented matrix, DFS.
okay. Yeah. So this is like the ABC of mathematics, kind of. Okay. So once we know how to multiply a row vector with a column vector or a row matrix with a column matrix, we can multiply two matrices. So I can take the first row of the first matrix, multiply it with the second, the first column of the second matrix, and this is going to give me the first entry of the product matrix, right?
Yes, ma'am.
That's how. Yeah. So if I have a 2 cross 2 matrix, 1, 2, 3, 4, the second matrix should definitely have 2 rows, at least 2 rows. No, it should actually have 2 rows, right? So
yes,
say 2, 3, 4, 5, 6, 7. This is a 2 cross 3 matrix. So what will the output be?
The output would be 2 cross 3.
2 cross 3 biometrics.
2 cross 3. Okay. So how do I multiply now? I only know how to multiply a row matrix with a column matrix. I don't know anything else.
I will take the first row of the
second column
and first column of the second
first
matrix.
column.
Yes. So I will do this for each of the columns.
Yes,
and then I'll get all these entries.
Yes.
And the same thing I'll do for this row with each of the columns. So I'll get these 3 entries. So this is the only thing that I know. This is the definition, how a row matrix is multiplied with a column matrix. And using this, I can multiply any 2 matrices. If you're not talking to me, can you please mute? Okay. So multiplication of matrices is clear, right?
Yes, ma'am.
Yeah. So this point we've already discussed. If I can add 2 matrices, then they should have the same rows and same number of rows and same number of columns. And multiplication, this m cross n with n cross p will result in an m cross p matrix, because the number of columns of the first matrix is equal to the number of rows of the second matrix. Okay. Yeah, so this question is just based on whether addition, multiplication and all that is possible. Can you add P and Q?
No, ma'am.
No, ma'am.
In fact, I cannot add P with any of the others, right?
Yes,
Yes,
ma'am.
yes.
And D also cannot be added with any of the others.
Yes, ma'am.
But Q and R can be
Q and
added
R
because
can be
they are of
added.
the same dimension. Yeah. So this is what is the order of P?
3 by 3.
Order
by
of 3
3.
cross 3.
Q is
Yes,
1 cross
1 cross 3.
1 cross 3.
1 row and 3 columns.
1 and
Yes.
3 column.
1 cross 3. It's
by 1.
3
cross
rows
1.
and 1
3 rows, 1 column.
Yeah.
We can
What are the
multiply
matrices
P
with
and D,
which?
right?
Huh?
We
What?
can multiply P and D, right?
Yeah. I was asking about addition.
Okay. Sorry.
Yeah. What are the matrices with which I can multiply P?
P.
Means
D.
P
and
into something.
P and D can be multiplied.
Only P and D.
Okay. P after P I can just multiply with P. But what are the matrices I can multiply P with before P? Like pre-multiplication.
Q
and R.
QR and U.
Q and R.
Q and R. Obviously, you can do P into P also. Because it's a square matrix, you can talk about the powers of the matrix. Okay. What about Q? After Q?
After Q,
D. T and D.
P and
D.
and D.
P.
Okay. Before Q?
R, D, and
Before
P.
Q,
R and P.
D.
R.
D only.
Only D.
only D, ma'am.
only D, ma'am.
Because the number of columns of the first matrix should be equal to the number of rows of the second matrix. So Q has 1 row. So the number matrices with only 1 column can be multiplied to get.
Yes.
Means only that is well defined. Okay. So yeah, you know things. So the matrix PD is of order 3 cross 1. Is it true?
Yeah.
Yeah,
Yes,
correct,
ma'am.
Yes, ma'am. Yes, ma'am.
Okay. If it's of order 3 cross 1, it cannot be of order 1 cross 3. QD. What is the order of QD?
1 by 1.
1 by 1.
1 cross 1. 1 cross 1.
QD. Okay. Oh, it's
Yes,
not 3 cross 3. It's 1 cross 1. Okay.
1%.
And DQ?
D by 3.
1
3
1.
by 3.
3 by 3.
3 by 3, ma'am.
Oh, 1 1.
3 by 3.
Q.
3
Yeah,
by
3
3.
3
3
by
cross
3 by 3.
3 by 3.
in QD. Sorry.
Is QD well defined?
So,
Yes.
Yes,
No.
ma'am.
Obviously,
Yes.
no.
that's why we got this option is true, right?
Yes, ma'am. QD.
No. Q is 1 cross 3. D is 3 cross 1. So well
QR
defined.
is not defined. QR is
QR is not
QR is
defined.
not
QR is
defined.
not
defined.
Not defined.
defined.
P plus Q is not
Not
defined.
Not defined, and the
P
P
is
is
not.
not defined.
Yeah.
Ma'am, option 9 will be correct.
Option 9 is
Uh,
correct,
No,
no, ma'am?
ma'am.
Oh, it's
Nine
not
and
defined.
10
Okay,
is
okay, fine.
Yeah. Correct.
Okay.
Ma'am,
Okay.
like when you're saying not defined, what exactly you mean, ma'am? Like, is it one
The
one
multiplication itself is not defined.
like
You
one
cannot
in,
even.
Perform the operation.
1 into 3 and 1 cross 3 that will result into 1 cross 3 that R and Q, right?
Which one?
QR 1
For
cross 3.
addition, we need the same order in both the matrices, right?
No. To multiply them, you need the number of columns of the first to be equal to the number of rows of the second.
Yeah, but for addition,
Yeah. Addition, you want the same order.
yeah, that's why it's not defined.
Oh, yep. For 9 and 10, yes. Is it clear why QR multiplication is not defined?
No, ma'am, I did not understand.
So for a matrix multiplication to be defined, the number of columns of the first matrix of, let me call it A, should be equal to the number of rows of B of the second matrix. So now consider QR. How many columns does Q have?
3 columns.
3. And how many rows does R have?
1.
They are not equal. So it's not defined, right?
Okay.
You cannot multiply.
Yes.
Yeah.
Excuse me.
Yeah.
In option 7, rows of Q and column of B are equals.
So it is defined, right?
So we should be right.
No, it's written it's not defined.
Ma'am, it should not be true.
Okay.
So it is defined. QD, the product QD is actually defined. So this is not true. Okay. So what is the order of QD?
One by one.
One plus one.
What is the order of DQ?
One by okay.
3 cross 3.
3 by 3.
Yes, ma'am.
Can these two matrices be equal?
No, ma'am.
No, right? Because if they are equal, firstly they should be of the same order, right?
Yes.
Yeah. So in general, matrix multiplication is not commutative. Means you cannot multiply them in any order you want.
Yes, ma'am.
That's clear, right?
Yes. Yes.
Yeah. But there are special cases where it is commutative. That is, QD will be equal to DQ. We'll see that you would have already seen in a lot of activity questions and all that where it is equal.
Ma'am, in case of addition in the same orders,
Yeah, addition is always the same, right? Because you can add in any order. You're adding it component wise only. But multiplication is not component wise, no? There's a different rule that we follow. That is why multiplication is problematic.
Then addition, like number of rows and columns, there is no relation. Like whatever columns I do have, I can just add into the next.
No, they should be of the same order. Both matrices should be of the same order.
Like it has to be square matrix. Square matrix.
No. They can be rectangular matrices, but they should be of the same order. Yeah. You cannot add a 2 cross 3 matrix with a 3 cross 2 matrix.
Okay, thank you.
The other one also has to be 2 cross 3. Okay. So suppose you have these two matrices. What is AB and BA? Can you do the multiplication? Let's do one of them and the other one will be clear. What is AB? How will you multiply A into B?
First row.
First row of A will be multiplied by first column of B.
Column of
Yeah. So you will do this
1 plus 0 plus
1 into 1 plus 0 into 0.
1 into 1 plus 0 into
0
0
plus
plus
4.
22.
Then this entry is
1 into 0 plus
1 into 0.
1 into 0, 0
0
into
into
2
2
plus
3 plus 0 plus
0 plus 0 plus
0. 8.
Yeah.
0
So you can fill the other entries, right?
Yeah.
Yes,
Similarly with second row and all that. And BA means you should write B first and then A. Both are well defined because they are both square matrices, right?
Yes.
Yes,
Yes, ma'am. Yes, ma'am.
Yeah.
ma'am. Just one request. Whenever you're sharing the PDF,
So is there any question?
whenever you're sharing the PDF, just share it with all the editing what you have done. So please,
Yeah. The same PDF will be there. Whatever I've written, everything, whatever the scribbling I do, everything will be there.
so that we can follow from there.
Yeah. Okay. So is there any question? Activity question, practice assignment, just the basics of matrices.
One general question. We talk about algebra function plus minus multiplication. Why we are skipping division of matrix or vectors?
So division of matrices is multiplying by inverse.
Okay.
Yeah. So
it's the same. multiplication.
Yeah, you don't divide by a matrix. Instead, you multiply by its inverse. Yeah. Okay. So how do we do this? What do we do here?
Ma'am, we will multiply A by A into A.
Huh.
And we will check whether it is
We
an
will cross-check,
identity
ma'am.
matrix or not.
Yes.
Yeah. So what do we get here? 1 into 0 plus 0 into 0.
It's
1 0 0 1.
1 into 0 plus 0.
It's 0.
So A squared is equal to I.
I.
Yeah. So it is clear that A squared equal to I does not imply A is equal to I or minus I, right?
Yes, ma'am.
A is not the identity matrix and A is not minus of identity, but still A squared is equal to I.
Yes, ma'am.
So you cannot do the splitting like you do in real numbers. If I have x squared is equal to 1 in real numbers, I know that x is equal to plus or minus 1.
Right.
But that doesn't that's not how it works with matrices. Okay, what about B squared?
B square is a zero matrix.
Yeah. So you get 0, 0, 0, 0. So B squared is equal to 0. Even though B is not 0, B squared is 0, right?
Yes.
Yeah. So this also doesn't work. So if I have a real number, say x squared is equal to 0, then I know that x has to be 0. But that's not how it works with matrices. You can have non-zero matrices whose squared is 0.
Okay.
So you have seen this kind of questions in activity questions, right?
Ma'am, actually there is a question in activity 1.2, question number 6. So ma'am, like
1.2.
Yes. Question number 6.
Okay.
Ma'am, like you just have shown the examples of that. In this question, will we have to like assume that kind of example, or is there any method to solve this? Like we'll take A to be A, B, C, D.
So if you have to, throughout the course, there is one thing that you should keep in mind. If you want to prove something, or if you want to say something is true, then you should give a proof. If you want to say something is false, it's enough if you give a counter example. So if it's not true for even one example, the statement is not true, right?
Yes.
Yes,
yes, ma'am.
If you want to say something is false, you just find one set of, or if you say all humans have 3 heads, it is enough if I find one human who doesn't have 3 heads, right?
Yes, ma'am.
Yes, ma'am.
Yeah, that is what this says. If I want to say every human has 1 head, I cannot just show that that human has 1 head, so every human has 1 head, right?
Yes, ma'am.
Yeah. So if I want to say something is true, I need to prove it. I cannot say that that person has only 1 head, so every human being on earth will have 1 head. But to say something is false, it's enough if I point out one thing which is false, which does not follow that statement. So in that context, the first one is not true, right?
Yes,
We just
yes.
saw an example. Yeah, so one example is enough to say that this is not true. Similarly, one example is enough to say that the second one is not true. What about the third option?
Third option is true.
True.
True, ma'am.
Yeah. So how will you say it is true? Can you take two matrices and then say that if I add them, I'm getting 0, so B is minus A?
No, ma'am. We can choose a general, like we can assume
Yeah.
A, B, C, D, right? Elements.
Yeah. So you'll assume A, B, C, D, and then B is some E, F, G, H. What is given is A plus B is 0. So A plus E is 0, B plus F is 0, C plus G is 0, D plus H is 0. So from these, I can tell A is minus E, B is minus F, C is minus G, D is minus H. This is nothing but B is minus E. Right?
Yes.
So this is the general proof. What about the fourth option?
Fourth option is true. It's true, ma'am.
Yeah. Why is it true?
Ma'am.
What is a scalar matrix?
It's
Diagonal
all
elements
diagonal
are a
elements are
constant.
same.
Diagonal
Same.
elements are
And
same.
constant. Yes.
Yeah. It's a diagonal matrix with all the diagonal entries.
Diagonal elements are same.
Yeah.
Yes.
And then now we are saying that when I multiply it with any matrix, any non-zero square matrix. When do you say something is non-zero?
None of the entry should be 0.
Should be 0.
No, not none of the entries.
At least one.
At least one.
Yeah. A matrix is non-zero
Non-zero.
if
When
it
at
is
least one of the
not the zero matrix.
Yes, ma'am.
Yeah. It will be the zero matrix when all the entries are 0. So it will not be the zero matrix if at least one entry is non-zero.
Yes.
Okay.
Can you come
So you
again
can
for
say
this non-zero matrix?
A matrix is non-zero when it is not the zero matrix. So if it is not the zero matrix, then at least one entry is non-zero, right? Not necessarily all the entries are non-zero.
Okay.
Yeah, like this one. This is a non-zero matrix, right?
Yeah.
Because it is not the zero matrix.
If it is not a zero matrix, then it is a non-zero matrix. Okay.
Yeah, that's it.
Mhm.
Okay, so A,
Ma'am,
B,
can you
C,
please
D.
prove it?
Which one?
Last option. This last option.
Yeah, I'm doing that. A, B, C, D, E, F, G, H, I. So when I multiply this, what do I get?
Alpha A.
Alpha A.
First entry is alpha A, 0, 0.
Alpha B, alpha C, and then alpha D,
Alpha Q,
alpha
E,
alpha F,
Alpha G,
alpha G,
alpha H,
Ma'am, also,
H, alpha I.
ma'am, also you can put it out alpha like outside and then.
Alpha times
yes,
the matrix
IB
B.
times it. Right.
Yeah.
Yes.
What about B times A?
Ma'am, it should be alpha Q, right?
No, that's in determinants. The B type.
No, that's in determinant.
It was 0. No.
Oh, that's determined. Yeah, right.
Yeah.
Even then, it won't be alpha cube. Even if
that's a lot.
Ma'am, here we don't need
No, if
to
it was
find
determinant, it would be alpha cube. But we are not talking about determinants here.
yeah.
So what is this?
This will also the same.
A alpha. Then should be B alpha, C alpha. Same, ma'am. Will come same.
Yeah, you'll get the same thing. So if it is a scalar matrix, I have proved for any general matrix B, A times B is B times A, right?
Yes, ma'am.
Yeah, in simpler words, B, if it is a scalar matrix, then B is equal to some alpha times identity, right?
Yes, ma'am.
Yes, ma'am.
Ma'am, please B into A. I want to show the B into A. B.
Yeah.
How is it possible, ma'am? We have to multiply first row into first column.
Yes. A into alpha plus B into 0 plus C
B into 0.
Then first row with second column. A into 0 plus B into alpha plus C into 0.
Okay.
Yeah. Yeah, so without the ABCD stuff, let's do this. So if B is a scalar matrix, then it's going to look something like this. Some alpha times identity, right? So
yes,
what is A into B? A is any matrix. A into alpha times identity. Can I write it as alpha times A into identity?
Yeah.
Yes, ma'am.
Yes.
And what is AI?
A.
You multiply
AI is
any
A, ma'am.
matrix with the identity matrix, you get this. Okay. What is BA? Alpha I. A.
Yeah.
So alpha times
IA, alpha A.
Alpha.
So these two are equal, right? Because these two are equal. So without the ABCD stuff, this is a simpler way of proving it. Is this clear to everyone?
Clear.
Yes,
ma'am.
Okay. Then any other question in AQ?
Question number 8, ma'am.
8. Okay.
Option 4.
So
Yes,
first
ma'am.
one, there
Same
exists some real number such that AB is equal to BA. Is that clear? Is it true?
Yes, ma'am. It is true.
Why? Can you give me one example, easy example?
Ma'am, simply we can take B to be zero matrix.
Yeah. Easiest example would be take it to be the zero matrix. Okay. There does not exist any real numbers. Okay. If one is true, then 2 is false. Okay. There does not exist any real matrix such that A squared is A. Is it true?
Ma'am, there exists.
Can you give me an example?
Ma'am, you can take A to be identity
matrix.
I square equal
Take
to I
the zero matrix itself. Again, zero is equal to. Yeah. Okay, there exists some real matrix such that A squared plus A.
Ma'am, second option, what exactly you mean? I could not catch you. Any real do not exist any real matrix means what exactly it means?
There does not exist any real matrix. Means for no two matrices A and B, AB is equal to BA. It's the negation of the first option.
Okay.
Ma'am, in third option also you can take another example like 1 0 0 0.
Anything, any matrix is fine.
Yes.
Okay, there exists some real matrix such that A squared plus A plus I is equal to.
I'm having same doubt in question number 9. Can you explain the same activity question number 9?
Question number 9, okay.
Yes, ma'am. Ma'am, how I'm supposed to find?
4. Ma'am, option 4.
Yeah, we'll do the option 4. What was it with 9?
Ma'am, how I'm supposed to find, ma'am? I am in question number 9, ma'am. Only one element of matrix A is given, ma'am. Then how I'm supposed to find, ma'am? If I'm multiplying a whole here in this, ma'am, it is asked, ma'am, 2 entry of matrix 2A plus B, ma'am. But I have only entry. Ma'am, in B I can find all the entries, but ma'am in A I am having only one entry, no? 1, 1.
No, but it's a scalar matrix, no? So if I know one entry, it's enough, no?
Yes, ma'am. If I'm multiplying 2, then if ma'am there is no any other matrix, ma'am, or means there is no any element. I'm not doing what element will be there.
Scalar matrix there will be only one value and they gave that.
Scalar matrix is a diagonal matrix, all of whose diagonal entries are equal. So I know one diagonal entry, so I know all other diagonal entries. right?
Okay, ma'am. I got it.
Yeah, it's a diagonal matrix. So you'll have only diagonal entries. And I know one diagonal entry, so all other diagonal entries are the same.
Okay, ma'am.
Okay. So what I want is a squared plus a plus I is equal to 0. So this is, have they mentioned any order? 2 questions. So you just start with any a, b, c, d. I want a squared plus a plus identity to be 0. So what is a squared?
A square plus BC.
A squared plus bc.
Then B whole into A plus D.
Okay.
Then it will be
CA plus CA square.
I guess I'll just write it down so that we can multiply.
AC plus DC.
AB plus BD, AC plus DC,
A plus DC,
BC plus D square.
plus D square.
Yeah. So I want a squared plus bc plus a plus 1 to be 0, right?
Yes.
AB plus BD plus B plus 1 to be, plus 0 to be 0.
Yes.
And then AC plus CD plus C plus 0. Equal to 0.
CB
Then BC
plus
plus
D square plus D plus 1 equal to 0.
So if I find just one ABCD for which all these 4 equations are satisfied, I'm done, right?
Yes, ma'am.
Yeah. You can randomly pick any numbers with satisfied. So maybe from here, B into A plus B plus 1 should be 0. From here, C into A
Ma'am, that is B whole into A
B
plus D. Ma'am, that is A plus D. Yes.
Okay. So shall I put just B and C to be 0? We'll see what happens. I'm just assuming. Yeah.
Okay.
And then if B and C is 0, this becomes A squared plus A plus 1 is equal to 0.
We get a complex number, not a real number.
Oh, yeah.
Solution.
Okay, then maybe we'll not put B or C to be 0.
A plus D plus 1 to be 0.
Yeah, let's put A plus D plus 1 to be 0. So say put A is equal to some 2 or what, minus, what should I, okay, 1 minus 2. It satisfies, right? These two equations.
Yeah.
A plus D plus 1. Okay, fine. Then what do I want? So, so these two equations are satisfied. And then B squared. Let's check this one out. So BC plus 4 minus 2 plus 1 should be 0. So BC should be 5 minus 2, 3 minus 3. Yeah, here what do I have? 1 plus BC plus 1 plus 1. BC is minus 3. Put any value, fine, right? 1 D to be minus 3. C. Everything is satisfied now, right?
Yes, ma'am.
Yes, ma'am.
Ma'am, actually no, in second equation, if we put B to be 1, then will it be, no, ma'am, it's satisfied.
No, this is satisfied, no, for me. So anyway, it's going to be 0.
Okay.
No, we chose such a way that it is all satisfied, no?
Yeah.
Yes.
For these values of A, B, C, D, the right hand side is 0. So the equations are satisfied.
So if I take this matrix, 3 minus 2. For this matrix, it is satisfied. A squared plus A plus I is equal to 0. This is not the only matrix, no, obviously. Because these are choices we made. We could have made different choices here.
Previously, we were taking in the second and the third equations, we were considering B and C to be equal to 0. But then we discarded that and taken A plus D plus 1 equal to 0. Why did we do that? Like, why
because when we took B and C to be 0, we were getting this A squared plus A plus 1 is equal to 0. That is satisfied only by complex numbers, right? We don't have complex numbers. Yeah.
Okay.
Ma'am, in such type of questions, we will have to find the values by hit and trial method only, or can we generalize it?
No, you can do this. There's no other way, no? There's nothing else you can do.
Okay, ma'am.
Okay. Okay.
Okay. Any other doubts in the activity questions? Others are pretty simple, I guess.
Yes, ma'am. In activity 1.3.
Oh, we haven't seen systems yet. Maybe we'll discuss systems and then come to this.
Okay.
Okay. So, yeah, systems of linear equation. There are basically only two, what do you call it? The basic problems in linear algebra, of which one of them is solving this Ax is equal to b. So you just want to solve Ax is equal to b. And you have already seen in practice assignment, graded assignment and all that, that there are a lot of real life problems which can be modeled into a system of linear equations. Unknowingly, we are actually solving a system of linear equations every day in our lives. So all those problems can be modeled as Ax is equal to b, where A is the coefficient matrix, the data and all that's given, b is the right hand vector, and x is the vector of unknowns for which we are actually trying to solve. We want to find out x such that Ax is equal to b. So yeah, when I write it down explicitly in the equation form, I'll have something like this. Here I have three variables, x1, x2, x3, and I have a system of equations. So this I can write it in the matrix form as Ax is equal to b, right?
Yes, ma'am.
How will I write the coefficient matrix A?
A11.
We will take the coefficient of
So you will first fix x. You will fix x to be the unknown vector, and the coefficients of x1 will be the first column of A, right?
Yes, ma'am. Yes, ma'am.
And the coefficients of x2 will be the second
column
of A, and the coefficients of x3 will be the third column. And the b1, b2, b3, that will be the right hand vector. So the coefficient matrix A, which is called the coefficient matrix, will be of order m cross n. What is m?
Number of rows.
Number of rows.
In the system, what is it?
Number of equations.
So the number of equations, the number of equations will be the number of rows of the matrix, and n is the number of variables. So this is how you write the coefficient matrix, and and there are multiple ways of solving it, of which you'll be studying a few in this course. So before trying to solve them, what do we usually do? If I have two equations in two unknowns, say I have x plus y is equal to 1, x minus y is equal to 0. How will I solve this?
We solve it using elimination.
Yeah, you'll eliminate one of the variables, find the value of the other variable, substitute it back in one of the equations, and get the other variable. So elimination and substitution, that is what we have been doing. And what does x plus y is equal to 1 represent in R2?
Straight line having intercepts.
It's a straight line.
1, 0 and 0.
Yeah. And what is x minus y is equal to 0?
Negative y-intercept.
It's a line passing through the origin, right?
Oh, yes,
Y
yes,
is
yes.
equal to
Right. Y is equal.
If I have two lines, and what are the possible things that can happen with these two lines?
Either they can intersect at one point or
They will either intersect at one point or
they will
not intersect at all. They will be parallel
or coincident.
They will both represent the same line.
Ma'am, mute all, ma'am.
Can you mute if you're not talking to me? So again, when we try to solve a system of equations, we have three possible cases. One is there may not be a solution at all. That happens when the lines are parallel. Another is we may have a unique solution, that is when the lines intersect. And the other is there may be infinitely many solutions where the lines are coincident. They lie on the, means they both represent the same line, and both the equations represent the same line. Is it possible to have exactly two solutions?
No, ma'am.
No, ma'am.
No.
Two lines cannot intersect at exactly 2 points.
Yes.
They either intersect at one point or they are one on top of the other. So these are the three cases, and that's what we will be seeing how to solve that using other ways. So yeah, before solving that, let's try to understand the coefficient matrix and all that. Okay, so here we have a system of equations. What will the coefficient matrix be? What will the variable matrix be? What will the right-hand vector be?
Ma'am, coefficient matrix will be
minus
2,
minus 2, 3, 1,
minus 1,
minus 1, 0, 1,
0, 1,
0,
0, 2, 0.
x1, x2, x3.
When a variable is
105.
missing, you put 0 as the coefficient, right?
Yes, ma'am.
105.
Yeah, so this what you're doing here is you're just doing matrix multiplication. Minus 2x1 plus 3x2 plus x3 is equal to 1. Yeah.
Right.
If I take the last row, then it's going to be 0x1 plus 2x2 plus 0x3 is equal to 5. So you're doing matrix multiplication here. Accordingly, you're just putting the coefficient matrix. Yeah, and then trying to solve. So we have a system of equations. We are trying to solve this system for different values of k. There is a k in general. Okay, how many equations do we have here?
3 equations.
How many variables?
2 variables.
Yeah, so what will the coefficient matrix, what will the order of the coefficient matrix be?
3 cross 2.
3 cross 2.
3 cross 2, right? Number
Yes.
of equations cross number of variables. Yeah. So you have 3 lines.
Yes, ma'am.
So if the 3 lines are like this, then there is no solution at all, right?
Yes, ma'am.
Because there is
No
no
common
common point of intersection.
Ma'am, come again.
If I have 3 equations, so I have 3 lines, right?
Yes.
If the 3 lines are lying like this, then there is no solution to this system, right?
Okay.
Yes,
like what?
You will have a solution if there is a common intersection point. These 2 lines are intersecting. This line is intersecting with this as well as this, but all 3 don't intersect at the same point. So there is no solution. Or even if they are like this, there is no solution. Or something like this, even then there is no solution. Yeah. There will be a solution if it is like this. Or there will be infinitely many solutions if both represent the same line and one intersection. Oh, okay. In this case, you'll have a unique solution, right?
Ma'am, I have a doubt.
Yeah.
what if two lines got infinite many solution and one line is intersecting both of the lines? How many
Yeah, that's
solutions
exactly
it has?
this, right?
Only one solution.
Only one solution.
One solution.
It's one
All
solution.
the three
Oh, okay.
lines intersect exactly at one point.
Okay. So it got one solution. Okay, thank you.
Yeah. So infinitely many solutions case will be all three lie on top of each other. Okay. So yeah, what is the coefficient matrix for this?
2, 3, minus
It's given
2k,
now.
4, 6.
The one given here, right?
Yes.
The right hand vector is 6, D, 12. Okay. And then
one more, like 2x1 plus 3x2 plus x3
Ma'am,
component also. Now, will it be considered as a line?
which one? Which one?
See, we have equation 2x1 plus 3x2 equals 6. So if we have x3 component, x3, x4, still it is considered as a line.
Yeah, it is a line in R3. That's it.
Then becomes a plane, no, ma'am? In
Oh
R.
yeah,
If
there
you
are
have
two free
planes.
vectors. Yes,
Yeah.
it will be a plane in R3. Yes.
It will be a plane.
Okay. Yeah, so how do we do this? So system has no solution if k is equal to minus 3 and d is equal to 0. What happens when k is equal to minus 3 and d is equal to 0? Minus 3 and d is equal to 0. What happens in this case?
There is no solution.
Why?
Because I think first and second
Because
equation
6 is
will
not equal to 0.
give
First and
parallel
second
lines.
Both are parallel lines.
Yeah.
Parallel line. Then
Left hand side both are
All
equal.
lines are parallel.
Oh yeah,
So
in
not
fact
all
this is
lines
also
are
a
the same.
multiple. The
Yeah.
first and the third equation are literally the same, right?
Yeah.
Yes, ma'am.
yes, and the
Yes.
second one will be parallel.
Huh. So when I put k is equal to minus 3 and d is equal to 0, I'll get parallel lines. So 2x plus minus 3x2 is equal to 6 means minus 2x1 minus 3x2 should be equal to minus 6. Only then there is a solution, right?
Yes, ma'am.
Yeah. So they become parallel lines, so there will be no solution. There will be a unique solution if k is equal to 3 and d is equal to 0. So k is
Yes,
equal
ma'am.
to 3.
Yes.
Yes, ma'am.
Yeah. So in this case, they'll intersect.
Ma'am, but
Fact,
since it is there are multiples, it could be like many solutions, right? Like how it is parallel. I didn't get
Yes, ma'am.
this.
They can be coincident also, ma'am.
Yeah, I didn't get
Which
that
one? Which
aspect.
one?
Actually, the first and the third equations, those
Huh.
are multiples, so they have to be coinciding, right? And not parallel.
Yes, yes, they are the same equation, right? They represent the same line.
Yeah, same line, collinear.
You just divide by 2
Don't
in
say
the third
parallel
equation.
because constants are different, no? Then only
No, they
parallel.
are the same, no? Even
No, ma'am, I'm
did I say they are parallel? 1 and 3?
Yes,
No,
yes.
no.
No,
ma'am.
ma'am. You didn't say
No,
that.
ma'am. It is collinear. Ma'am,
Ma'am,
I'm
so
asking.
then how come no solution for the second option? I didn't get that part properly.
The no solution thing is coming because of the second equation. 1
Yeah,
and 3 are the
three
same
look, we are not
equation,
able.
so that's not going to make any difference. The second equation is what is coming from here. So the second equation becomes minus 2x1 minus 3x2 is equal to 0 if k is equal to minus 3 and d is 0, right?
Yes, ma'am. Okay. Yeah.
Now they are parallel lines, right?
Yes, yes. Right.
This one and this one. Yeah.
Yes.
Option 3 is true because I will have a unique solution when I solve. So what is the unique solution? 1, 3 by 2, is it?
Yeah.
Oh. And then the system has infinitely many solutions if k is equal to minus 3 and d is equal to 6.
No, minus 6.
minus 6. For option 5,
when
it
it
will
is
be
equal to
correct.
6, there will be no solution, right?
Yes.
When it's minus 6, they will all represent the same line, and then there will be infinitely many solutions. Is it clear to everyone?
Ma'am, when it is 6, ma'am, when D is 6, then it will have unique solution, na?
No.
K
When D
is
is 6
minus
and
3.
K is minus 3,
Yes.
2x1 plus 3x2 is 6, minus 2x1 minus 3x2 is 6.
Yes, ma'am. It will have unique solution, na?
No, they are both.
No solution. These are two
No,
parallel.
no, they are both
these,
parallel.
the left hand side is the same, no?
They will become parallel lines.
You multiply with the first equation with minus 1, you'll get this part, but you won't get this part. You can just plot 2, 3. So this is 3, this is 2. This is one line. This is the first line. The second line is minus 3 minus 2. Minus 3 minus 2. Or minus 3 minus 2.
Oh, yes. Yes, ma'am, got it.
Yeah.
Ma'am,
When
ma'am,
it
can
is
you
minus
just,
6, they will be the same line.
Okay. Ma'am, can you just give an example of equations like you just have drawn you just have draw the picture, so the graph of that.
So
just,
the same.
Ma'am, where we will get like we take 3 equations. For any of 2, we will get a solution, but will not get a common solution for all 3.
Like this, right?
Yes, ma'am.
So we should construct this y is 1, x minus y is 0. So then I guess this should work.
Yes.
Or we can take the 3 points and make 3 lines by joining 2 points.
Yeah. Take any 3 points and then find out the equation of the line joining them. That's you'll get 3 equations. I think this should work. These 2 have a solution. These 2 have a solution. These 2 also have a solution. Yes.
So, ma'am, from here, I think we just need to check for every option where it is shown like it will have a unique solution or not.
Yeah. Like here, that is how you should do, because K is not given, no? So based on each option, you should work out separately.
Okay.
So any doubts in system of equations?
No, ma'am.
Madam. Hello, ma'am.
Yes.
Could you repeat question number 6, ma'am? Activity assignment 1.2. Just you have cleared that last option of this question.
For that A squared plus.
Yeah. Question number 6, 1.2.
Oh, the scalar matrix thing. Is it this one?
No, madam. Question number 6. I think question number 8. Yes, madam. Yes.
So in this,
AB is equal to BA.
is...
Yeah. Last.
Which one do you want? Last option.
Last and first, madam. Both.
Okay, there exists some real matrices such that AB is equal to BA. Can you give an example of a matrix for which the first one is true?
A is equal to matrix A is equal to A, B, C, D. When we multiply A and the same matrix with A, then AB is equal to BA. We can
squared, right?
We can get this as B equal to B. Okay, madam.
Fine. What about the fourth option? I want to check whether there exist matrices such that A squared plus A plus I is equal to 0. Right? So I'm just checking if that is possible. For that, I'm taking A to be any matrix, A, B, C, D. And then finding A squared, and then I'm just writing this. I want this to happen. So entry wise, I'm writing it down, what is needed.
Yes.
And then I'm doing trial and error and trying to find out 4 numbers A, B, C, D such that all 4 equations are satisfied. That's it.
Okay.
Yeah. So is it clear how these equations came up?
Yeah.
Yeah. This is A squared plus A plus identity. So from that equal to 0. So I get 4 entries of this matrix. It should be equal to the 0 matrix. So all the 4 entries should be 0.
Okay.
Excuse me, ma'am. Hello.
Yes.
Can you hear me? Hello.
Yeah.
Yes. So, ma'am, like basically in this type of questions, there is no way to exhaustively check that whether I have eliminated all options or not, whether it must be true or must be wrong. Like I can always feel like, what if there is some other example which I can't think of? Something like that.
No, here you just have to check whether there exists or not. So I have given a set of values for which
like here
everything is
we have
satisfied.
done in exam like some other equation, some other form if it comes there. There in the exam hall, how will like to conjure up an example out of it, like immediately, like okay, this example does not fit the question, so option is right or wrong, like that.
Ma'am, here there are 4 variables and we have 4 equations, so we can find 4 solutions to all those 4 variables. So
No,
I
this is
think
not
it's
linear. No, these are not linear equations. Quadratic.
In this question, ma'am, we have to only get the one set of values for that this equation is true.
Yeah.
So
even in the exam, when you have such type of questions, we give you questions where you can easily identify. Like, see, for example, if I had told that there exist matrices, diagonal matrices, such that this is satisfied, then that was not going to happen, right? When I put B and C to be 0, I was not getting a solution, right?
Yes, ma'am.
Yes,
yeah. So when you just write down the given information, you will be able to solve it.
Like at some step of the process, we will get some hint that okay, it's true or not.
Yeah.
Okay,
so, ma'am, in place of A, I can take any number and also solve, right, to check?
Yeah, but how will you don't know, no, whether if you take any number here, or you're telling just in the place of A, you will put some number, is it?
Yeah, like for example, A, B, C, D would be 5 or 6, like -1, 2, or any random numbers and check.
Oh, no. See, if you put any random numbers, you don't know whether you will end up with such a matrix, right?
Exactly. So then
It's very unlikely that you start with such a matrix. So the best thing to do is start with general things and then try to get some values for ABC, just like how we did.
Achha. Okay, ma'am. Okay.
Yeah. Because if you start with random numbers, there is no guarantee you will end up with such a matrix.
Okay.
Excuse me.
Activity.
Yes.
I don't know whether it has been discussed earlier because I was outside for a moment. Can we consider that A square plus A plus I as a quadratic equation, and then it's like b square is greater than or something like that. So can we
No, you
determine
don't
like
have
that?
a solution. No, you don't have a solution to this. You don't have a
Mm-hmm.
real solution to this.
Okay.
But there are real matrices which satisfy this. That's what we have shown, no, ultimately.
So it's like we cannot do in that pattern.
It's the. Can you repeat?
I mean, it's like it is in the form x square plus x plus 1 is equal to 0.
Yeah.
So it's like we can find whether a quadratic equation got real roots or not. So can we do like that?
No, but does this equation have real roots? X is equal to minus b plus or minus root of b squared minus 4ac by 2a. Does not have real roots, right?
Okay. Yeah. But
But
when
I
it
did
comes to
find a real
matrix,
matrix satisfying this, right?
okay,
Yeah.
okay. So we cannot
Exactly.
go by okay. We cannot judge by that criteria.
Yes, yes.
Okay.
It's similar to this. X squared is equal to 0 implies x is equal to 0. But the matrix doesn't satisfy this.
Oh, yeah. Okay.
Hello, ma'am.
Yeah. Yes.
Ma'am, activity 1.3.
Okay.
7th question.
Okay.
1.3, ma'am.
1.3. Okay.
7th question.
Okay. Is everything else 1 to 6 is fine, right? All simple.
Yes.
Okay. So how should we do this?
Yeah, ma'am.
You tell me what I should do. Okay, if I have AX is equal to B, what am I trying to find out from here?
I didn't get the question.
Ma'am, x1 and x2 are the solutions.
I want to find out X, right?
Yeah.
The solution to this is X because A is a known, B is known. X is what I should find out. So X is the solution to AX is equal to B. So if I say Y is a solution to AX is equal to B, what will it mean?
AY equal to B.
Yeah. If Y is a solution, then AY is equal to B. Okay. Let X1 and X2 be solutions of the system. Okay. So what does it mean if X1 is a solution?
AX1
AX1 is equal to B. And AX2 equals to
And AX2 is equal to B. This X1 and X2 is not X is equal to X1 and X2 here. This is not this. X1 is a solution to this system. X2 is a solution to this system. So now can you solve?
Here, ma'am, here X1 and X2 are column matrices.
Yes.
Yeah. It will be a this is a column vector, this is a column vector.
Ma'am, also here AX equals to B is a linear equation which has infinitely many solutions. Is it?
Is it given? Oh, you're telling
No,
because
ma'am.
there are two solutions, there are infinitely
Yes.
many, is it?
Yes,
No, but
ma'am.
X1 and X2 may be the same, no? Nobody
Ma'am,
said that they are different.
No, ma'am. Actually, we can say it now because no solution can have two solutions. No linear equation can have two solutions.
No. X1 may be equal to X2, no? In that case, it is a unique solution, no?
Okay. Yes.
Yeah, but or they may be both zeros. So in that case, any scalar multiple will also be zero. Yeah. Okay. So I have this. What
Hello,
can
madam.
I tell about AX1?
Plus X2 is 2B.
Okay.
Yeah. This should be 2B.
Yes,
But what if my B was 0? Suppose B is 0. And I have two solutions. Then
it will remain 0 every time.
So x1 plus x2 is also a solution, right?
Yes, ma'am.
Oh, yes, ma'am.
What about alpha times x1?
It's also solution then.
Yeah. So if I have this is called a homogeneous system, right? When B is 0, it's called a homogeneous system.
Yes, ma'am.
So if I have a homogeneous system and if I have a non-zero solution to it, then any scalar multiple of that is also a solution.
Ma'am, I think we'll get this in the week 2 content.
Yeah. You'll get this in week 2. Yes.
So, ma'am, what is a homogeneous system?
When the right-hand vector is 0.
Usually in equations, the right-hand side is 0.
Ma'am, like how did you assume that the two x1 and x2 are same, like over here?
Where? Here.
No, like you gave some example initially, no? So that I didn't understand.
What did I tell?
Ma'am, like you said, x1 and x2 can be 0. The question I have asked to you, like.
Okay. So the question was, since there are two solutions, there may be there are infinitely many solutions. But then I was like, it does not say there are two different solutions, right? They may be the same solution. That's what I said.
Hello, madam.
So if they are the same solutions, that doesn't mean that there are two intersecting points or anything, right?
Ma'am didn't get that much actually, not so clear.
Okay. I think you can ignore that for now.
Okay,
it
ma'am.
was something that,
Hello, madam.
Yes.
Madam, can we say that a zero vector is a scalar vector? Some special cases, can we say
No,
that?
what is a scalar vector?
No, a scalar matrix. Sorry, madam, a scalar matrix.
Yeah. This is a scalar matrix, yes. Because this is a diagonal matrix whose diagonal entries are equal.
Ma'am, but in diagonal matrix, we said that diagonal element should not be 0.
No. In a diagonal matrix, other than diagonal entries, everything else should be 0. Nothing is said about the diagonal entries.
Means the diagonal entries should be same. Means.
Okay.
No, for a scalar matrix, diagonal entries should be same. For a diagonal matrix, just other than the diagonal entries, everything else should be 0. Nothing is said about the diagonal entries as such.
So can we say that a scalar matrix is also a diagonal matrix, but a diagonal matrix cannot be always a scalar matrix?
Exactly. Because for a diagonal matrix, the diagonal entries need not be the same. But for a scalar matrix, obviously it is a diagonal matrix by definition itself.
So identity matrix satisfy both of the three of the criteria.
Yeah. What is the third criterion? The 3 in the sense?
Like I mean that's identity. I mean every diagonal element should be 1.
Ma'am, can you explain the infinite solution, unique solution, no solution with the diagram? So I'm still confused with that.
Yeah, okay. So let's take one of the activity questions. So is the 8th question also clear? How to solve the 8th question? Here we have two systems, that's it. Right?
Yes, ma'am.
Yeah.
Yes.
Then this, okay, fine.
Ma'am, question number 10 also, I have doubt on that.
Okay, we'll finish question 10 and then get to the figure part of it. Okay, yeah, what is the doubt in question 10?
Ma'am, actually I didn't get the meaning of the question here.
No, you just solve system 1, solve system 2 and then plug in the values and get MN. There's nothing else, no other relevance.
Yes, ma'am, I did that and also get the correct answer, but what is asked here, I don't know.
No, there is no relevance to the way it is written. There is no relevance. It means, yeah, even I was thinking like why the coefficients from this system and this system, but it has nothing to do with it. You just plug in the values for x1, x2, x3, x4 and solve. That's it. Okay. So, yeah. So there was someone who asked about figure and yeah. Okay. So in this case, the first figure, figure A, how many? So when do you say a system has a solution?
When there is an intersect point,
yeah.
Common to all the equations.
Yeah. So this is a line which is say equation 1. This is another line, equation 2. And this is the third line, equation 3. So I have 3 equations. And if there is an intersecting point, it means that that point satisfies all the 3 equations, right?
Yes, ma'am.
And that is when it is a solution. The unknown vector, that x1, x2, x3, or whatever is the unknown vector, should satisfy all the 3 equations, all the equations. Then you say that there is a solution. And that will happen geometrically when there is a common point of intersection for all the lines, right?
Okay.
Yeah.
Okay.
So suppose I have 2 lines like this, parallel lines, will they ever intersect?
No.
No, ma'am.
So there's going to be no solution at all, right?
Yes, ma'am.
Yes.
Suppose I have 2 equations which represent the same line. Are they intersecting at any point?
Yes, ma'am. Infinite points.
Infinite.
They're intersecting on all the points of the line, right?
Okay.
They're one on top of the other.
Okay.
So in this case, there are infinitely many solutions. So is it clear from these 3 figures?
Yes, ma'am. Yes, ma'am.
The first one does not have a solution.
Yes,
The second one has a solution.
Yes.
And the third one, infinitely many, means assuming that both the equations represent the same line, right?
Okay.
Yes, ma'am. We can also say that if lines belongs to the same family, then there must be a solution, particular solution.
Yeah, but what is the definition of a family and all that comes into picture, right? Like, what do you mean by telling they belong to the same family?
Family of lines means all the lines intersecting at the same point.
Okay. If that is the definition, then yes, they have a solution.
That means concurrent lines means.
What does concurrent line mean? Concurrent line is what was concurrent lines? I forgot. Concurrent lines.
I guess, ma'am,
Lying on the same
lines
place,
are,
is it?
yes.
Coplanar. Plane means
coplanar lines.
So coplanar lines need not intersect. No, they lie on the same plane. That's it. That's it, right?
Yes.
But I think concurrent meant they intersect, right? I don't remember.
At the same point.
Like concurrent, passing through same point.
Same point.
Okay. Then yeah, if they pass through the same point, then yes, they intersect.
Can you explain that on a plane in 3 lines, whether they have a unique solution or infinite many solutions?
This is unique solution, right? 3 lines having a unique solution.
This is in R2. If I wanted to see it in R3, there is a confusion to how to read that graph.
So in R3, okay, let's go to GeoGebra. Okay, before going to GeoGebra, these planes don't have a solution, right? This represents an equation with 3 variables. This represents another equation with 3 variables. They are parallel, so they don't have a solution, right?
Yes, ma'am.
Okay, we should choose lines which intersect. From that K problem we can do, right?
x1 minus 3 x2 is equal to 4.
x1 minus
3 x2
equal to 4. Yeah, so this is a plane, right? it visible? The plane.
Yes, ma'am, it's visible.
Okay, I'm writing it in. Oh, the K equation, K problem didn't have 3 variables, is it?
No, it is 2 variable, ma'am.
Oh, okay. Okay, we can plot it in 3D. What is the other equation?
3x1 plus kx2.
3x1 when K was minus 3.
Minus 3,
and
x2
D was 6.
0.
So here we can see that they intersect, right? And at how many points are they intersecting?
Infinite points.
Yeah, because there is no. I'm having only 2 variables. I haven't put the z at all. So because of that, they along this entire line they are intersecting, right?
Yes, ma'am.
Ma'am, I don't see it. Can you please explain it again?
Yeah. I'll change
Yes,
the
ma'am.
color.
Please explain again.
So now can you see that they intersect at infinitely many points? This is one plane, the blue one. The pink one is another plane. They intersect here, right? Along the plane, along the line where the pink changes to blue.
Yeah.
Okay.
Yes.
So, ma'am, you are considering it for a plane.
Yeah. I have only 2 variables. I am plotting it in R3, which means that my z coordinate is 0, right? Means in my equations, my z is missing. That is why I'm getting something like this. So is it clear that along all these points they intersect?
Yes, ma'am.
Yes,
So
ma'am.
infinitely many solutions. Let's change this equation a bit. A plus z is equal to 0. Here, that's 2z, something like this. Okay, again I'm going to get planes, but they are 2 different planes now. Let's put one more equation. Minus x plus 3y minus z equal to 4. These will never intersect, right? Because these are parallel and this intersects both of them. But since these 2 are parallel, they're never going to intersect, right?
1, 3 not intersect.
Huh?
So the pink one intersect the
Equation 2 intersect.
Yeah, but when I have a system of 3 equations, there is a solution if all 3 intersect at the same point.
So,
right?
ma'am, equation 1 and 3 will not intersect, right?
Yeah, because equation 1 and 3 are parallel, right?
Yes.
It's clear. I have multiplied by minus 1 on the left, but not on the right.
Ma'am, in this, did you select the color for the third equation or it gave automatically because it was parallel?
No, it's always blue by default. I haven't changed.
Okay.
Now is it clear?
Yes, ma'am.
Yeah. Say I give minus 4 here, which means they will be the same plane. Now they are both the same, right? The blue and green are the same. That's why the color is flickering.
Yes.
And say.
In this case, this is a infinite many solutions.
Yeah, because the equation 1 and 3 are the same, and then the plane intersects along the line of intersection.
Okay.
Ma'am, show example for unique solution.
We need to construct.
Sorry, ma'am. Could you go back again in the ones where these 2 blue and the green were overlapping? That's the second and the third were overlapping. In this case, there's one unique solution, right?
No. Infinitely many solutions along all these points.
Okay, because it's a plane.
Yeah, this is one plane. This is another plane. You don't have a third plane. It is that on the first plane itself. So wherever they intersect,
if this was not
solution,
in a plane,
right?
then it would. If this was not a plane, it was just a equation. Then even then.
No, if there'll be a unique solution case as well, which I.
Oh, because this is 3 variable, that is why there will be infinitely many solutions. But if it was a 2 variable one,
it would have had a unique solution. This point would have been the solution.
Yeah, okay.
I can do this. Z is equal to 0. Now there is a unique solution, right? This is that solution. Z is equal to 0 means on the xy plane. So wherever these 3 planes intersect, this is my unique solution.
And what's that point, ma'am?
We have to see. How do I see that? How do I select the point?
Z will be 0
It
in
should
that point.
be 0 here, and I put 0 here, and then I subtract these two. 2x will be minus 2, so minus 1, comma, minus 1. We'll go that side as plus 1, 5, minus 1 by 5, or minus 5 by 5. And then 0. It's not this point. Okay, my calculation was wrong. But this is the point, right?
Yes.
Ma'am, it will be 1
we can
minus 1 and
calculate
0.
actually. We'll move forward.
1 minus 1 and 0.
1 minus 1.
That is 1. X coordinate
1.
will be 1.
Yeah. So the point, this point is the point of intersection of all the 3 planes. Is it clear what happened when z becomes 0?
XY plane.
We are on the xy plane. So my intersection will be like in the 2D case. When z becomes 0, in these 2 equations, z becomes 0. And in R2, how we solve system of 2 equations, that's how it works.
And actually, last time also they tried to use Desmos, and finally they taught us how to draw graph without Desmos use. Here, here without this calculator, is it possible to visualize with pen and paper how we can?
Yeah, like what we did here, like this.
Because after one session, we never started using Desmos. We stopped using Desmos because we knew how to draw the graph ourselves.
Okay. Here we don't need all this actually. GeoGebra is only making things
visualize. That's all.
More visual. Yeah, you're only able to visualize better. Nothing. You don't even need all that here.
Yeah.
Okay. Any other doubts?
But in the future weeks also, it won't be required.
Ma'am, 9th question.
Yeah, 1 second. In the future as well, we will not be needing GeoGebra, but it's just that it will help us see things better.
Okay.
Yeah. Okay.
Ma'am,
9th.
ma'am, suppose.
Yes.
Ma'am, suppose you take a 3 by 3 matrix. Then how do we check that the solution has infinitely many solutions by just pen and paper?
You will learn the methods in week 2. The methods by which you can check whether there are infinitely many solutions, unique solution, all that will come.
Okay. Ma'am, 9th question, please.
Ma'am, I have a question. If there are 3 in a system of equations, there are 3 equations but 2 variables. I think the question we had done that KD was such. Then in that case, if 2 lines, 2 equations are exactly the same, I mean, they're multiples of each other, that means they'll be overlapping and they'll be intersecting one of the, let's say, the 3rd line. So in that case, there would be only one unique solution?
No.
Yes.
Oh, you overlapping, yes.
No, 2 lines are overlapping, and the 3rd one is intersecting at one point.
Like this, right?
Yes. No.
Overlapping. So like on top of this. Yeah, there'll be a unique solution.
But then if we have 3 variables, then we will have infinitely many solutions.
Still one.
Can you please repeat the
When,
question
yeah,
that you
when
asked?
you have 3 variables, you'll have 2 planes intersecting, right?
Yes,
This will
yes,
be one
yes.
plane.
Yes.
This will be another plane.
Yes.
So there'll be a line of intersection.
Ma'am, what was the question?
Yeah, so there'll be infinitely many solutions, right?
Yeah. So the
how, ma'am?
question was
Can
this.
you go back? See.
I'll show it here. Minus minus x plus 3y minus z equal to minus 4. In this case, the blue and green is because the first and third equation are the same. And then pink is the second equation. So the point of intersection is all these points.
Straight line.
Okay.
All real
And by,
numbers lying on that line.
Yeah.
By just looking at the equations, we cannot say that it will have unique or infinitely many. We just need to solve it, ma'am. Is it?
Yeah. No, by looking at it, you can tell. By end of week 2, you can tell.
Oh, okay.
Yeah, okay. So let's do the 9th question. Consider a system of equations. If the given system has a unique solution, then K should not be equal. So what should it be? What is the doubt here?
Ma'am, actually this question was elaborately done yesterday.
Oh.
Or day before. I mean, almost 15-20 minutes was put on this question by sir.
So the person who asked doubt in this question, can you watch that? Do you want me to discuss?
Okay, ma'am, I will watch it.
Once you finish all your topics.
One more question. Practice
Yes.
assignment.
Ma'am, 1.47.
It's like practice assignment question number 8.
Oh, 1 second. 1.4 we haven't covered, right? Determinants we haven't covered.
No, we haven't covered it.
Okay, I'll come back to that. Practice. Yeah.
Question number 8.
Okay.
How to approach this? Getting the matrix.
So did you write down the matrix from the given information?
Which I started, it was wrong. Like that is the reason I'm not getting the right solution.
So you want me to solve this? I think the solution is already up. Maybe you can check that. Maybe you can check in the solution. You can see the solution here.
Okay.
Yeah. Any other doubts?
Hello, madam.
Yes.
Madam, actually, if we take two matrices A and B, and we have seen that A into B is equal to 0. If A is a scalar matrix and B is a non-zero matrix, then A is equal to 0. Why only A is equal to 0? Why not we are saying B is equal to also 0? Okay.
No, B is given. No, it is non-zero.
Oh, B is non-zero. That's why it is not.
Yeah.
Okay, so a scalar matrix is equal to 0. Okay, madam.
Yeah, you'll get some. It will be something similar to this that we discussed.
Yeah. Okay. I'll find it.
So
hello,
what
madam.
it basically tells us, the product is 0. It says.
Yeah,
but
yeah.
A is not 0. Alpha has to be 0.
Oh.
Okay.
Oh.
Any other doubts?
Ma'am, I have a doubt, ma'am.
Yeah.
Ma'am, can we add two determinants, ma'am? Like in determinant A plus B equals to determinant of A plus determinant of B.
You tell me the answer.
Ma'am, like we do for no, ma'am, I'm confused, ma'am. One particular question, ma'am. we know that one determinant of A into B is determinant of A into determinant of B. It is same applicable for addition part 1.
I'm saying it is not. Can you give me a counter example?
No, ma'am, I don't have such one. No. Again, ma'am.
Quickly think and tell, no? Quickly. Simple examples. Take one matrix to be this. Think of another matrix such that determinant of this plus determinant of this is not equal to determinant of A plus B.
Another, ma'am, you have talked about if a matrix square equals to the matrix value.
So you answer this no first.
Ma'am, can you repeat once again?
Your question was determinant of A plus B is not equal to determinant of A plus determinant of B. Means you wanted an example for that, right? Take A is equal to this. Can you quickly construct a B such that determinant of A plus B or say equal to 0, but determinant of A plus determinant of B is not equal to 0.
And can I take B matrix as a 0 matrix?
But in that case, the determinants will be the same, no?
Take a scalar matrix.
Ma'am, could you please introduce the basics of determinants before we take questions so that we're clear on this?
Okay. We'll discuss determinants in the next session. Both the lectures on determinants. Yeah.
Thank you, ma'am.
Yeah. So you can maybe take this matrix, right? What is A plus B? A plus B is 0, right?
Yes.
So the determinant of A plus B is 0, but determinant of A is 1, determinant of B is 1, so not equal.
Yes, ma'am. And another part, when you talked about A square equals to A, when A square matrix equals to A, ma'am, is it possible for every condition or it is just for an identity matrix?
No, why? Minus what A squared is equal to A, 1, 0, 0, 0. So this A squared is A.
Yes, ma'am. I was having doubt because in graded assignment there is a question in which I am getting confused.
Okay, what is the confusion about?
Ma'am, in graded assignment, when there is an equation which involves identity matrix and there is an equation which we need to solve and find the value of m. So I was assuming A square equals to A is only possible for usually identity matrix.
But that's not the case. No, I gave you an example of a matrix.
Yes, ma'am. You have given the example, ma'am. Then again, one question has arisen: what would be the matrix? Means, I can take any matrix, ma'am.
Yeah, if you want to prove something, you cannot randomly choose matrices and tell that for this it holds, so it has to be this. Which question? Okay, maybe let's not discuss graded now because the deadline is not yet over.
Ma'am, but there is a simple doubt of a symbol, ma'am. In question number 9, ma'am, there is a symbol.
This one
X. Yes, it is the third one, ma'am. Where we need to find the value of m. So I'm assuming I as an identity matrix, of course, but I was also assuming A square equals to A as an as A as an identity matrix.
No, you cannot assume that. A be any square matrix such that A squared is equal to A. So you cannot assume A is identity. I gave you an example of a matrix where A is not equal to identity. So this is for any matrix A satisfying this. So you cannot assume any particular matrix. You should try to solve this.
I mean question number 9, ma'am, there is a symbol x raised to the power bar. Ma'am, what does that mean actually?
In which question?
Below this, yes, ma'am. If x raised to the power bar, then what does means?
No, it's just x prime. Instead of x prime, take y. That's all. It has it's not anything related to x. X prime is another solution. That's it. Or
It's
is
just
it
it is the solution of above linear equation. It is already
ax is equal to b. Yes. Yeah. Whatever is the thing.
And again, when we are taking in the determinant, if we are putting in a whole square, means like in determinant a plus b whole square, then can we break it as a formula, ma'am?
What determinant?
For an example, determinant of a plus b whole square.
Okay.
Then can we break it as a determinant of a square plus 2ab plus b square? Can we do such things, or it is it won't be
You
there?
cannot do for this reason, no?
Excuse me, ma'am. Hello.
It's not even equal to 2ab. Yeah.
Hello. In many such questions, I've also encountered this situation where we had to simplify the expression, like assuming it is just a variable and then putting values. Like even like finding values of m or k, we had to simplify the expression, and where a and b were metrics, but we were treating them just like variable. Like
No, like can you give me tell me a question where?
Yes. 1 second. Just number third of the same graded, for example. Okay, let me find in practice assignment. 1 second. It was there in graded third number was like that only.
Can you tell me the question, because
third number, ma'am.
No,
the
question.
type will be the same. Yes, type is same. That like this similar type which is here. Like I am simplifying.
Yeah, so you cannot
using...
assume A is some matrix. This is a question which is asked for all matrices such that A squared is equal to A.
In general, yes.
So this I plus A whole cube, we cannot open up the like with the formula.
You can. A of... How will you find out A plus B whole squared? In the same way, you can open I plus A whole cube.
Yeah, that's what I was also asking.
But we can use other methods also, no?
No, you do anything, you just get the answer. Yeah. But you cannot assume that A is equal to something.
No, just like A will remain A.
Yeah. You have to use the fact that A squared is equal to A. That's it.
And I can be replaced with 1, or we should leave it as such in case solving problem?
No, you cannot add a matrix with a number, right?
No, like while multiplying a matrix like A into I, it's same as A into 1, right?
No, it's A into the identity matrix. Yeah, even though it is equal to 1 times A, but that's not what it means.
Okay.
You're multiplying the matrix with the identity matrix.
Because I kept replacing with 1 and I was not getting answer. Ultimately, I left I as such, and then the answers were matching.
Yeah.
Okay. Thank you, ma'am.
Okay. Any other questions?
Ma'am, 1.47.
Which one?
1.47.
1. Oh, we haven't discussed 1.4, right?
Yeah. Yes, we have not discussed it.
Ma'am, can you need a PDF, ma'am, first, so that...
I think we'll stop here. We'll continue in the next session, Tuesday's session. The last 2 lectures we'll discuss in the next session.
Okay. Noted.
So I told you, we'll split the tent so that it's not a lot for one session. Question 7. Yeah, so this is given, right? This is how you calculate the Yeah, you just plug in the values and find out. You find the determinant, half determinant of D, half mod determinant of D. This question is discussed in detail in this course. You can check there as well.
Ma'am, one more suggestion, ma'am. Sorry, I'm
In which
interrupting the other student. When you
in discourse, in discussion forum.
Okay.
And when you upload the PDF, what you have given, can you upload the blank PDF? Also, the whatever the notes you wrote. So you solve. Can you make it two?
Yes.
Because I want to solve one.
I will upload this one in which I have written all this.
The blank one also. Can you...
What do you mean by blank one?
This PDF, ma'am, which you sent, we can erase it using this browser only, the ink, but it took a lot of time.
No, why? Because I want to solve
but why do you
myself
want the blank PDF?
I want to solve myself.
Is it possible? I just put all this content from Solve With Us, so you can just take that. Solve With Us is there, no? This is just from Solve With Us. Where is the Solve With Us? This one.
Oh, okay.
So you I just took it from. Yeah. It's Solve With Us is basically the summary for the entire week, right? Yeah.
Would you be continuing with the Tuesday session?
Tuesday, I don't know. One of us will be taking.
Okay.
Either Shubhajit, Shubham, or me.
Okay. Fine. Thank you.
Madam, where can I find the PDF that you're using currently? I mean, the one where you are solving these problems.
I haven't uploaded it yet. After the session, I'll upload it. You will get it in the supplementary contents part.
Thank you. Thank you.
And also, this graded assignment, and can you upload the PDF one? Because generally, we can download the PDF. Sometimes when we get some.
But it's usually like this, right? We will upload the solution PDF, but questions will be on the portal, right?
No, before it was PDF question paper also was there. Sometimes it will be helpful when I get some spare time in my office. Otherwise, I have to work for another day. Yeah.
Okay. I'll check with the team. If it was happening earlier, we will do it this time.
In CT, they used to share, ma'am, the question PDF.
Question PDF, sometimes.
Yes, in madam, maths, if it was happening earlier, I don't think it was happening earlier, but if it was happening, we will do it.
Ma'am, for practical assignment, solutions are not available on dashboard. What you showed previously.
Now it is uploaded.
Practice assignment solutions is there in the supplementary contents. Practice assignment solution. Then from this, you'll get the drive link. Okay, so shall we close the session? Yeah.
Yes, ma'am. Thank you very much for the session.
Can I ask a doubt?
Thank you, ma'am.
Yeah, sure, please.
Thank you,
Hello,
ma'am.
You can leave. The others can leave. If you have a doubt, you can stay back.
Yes, ma'am. I have a doubt in the linear equation, ma'am.
Yes.
So regarding this linear equation, which we have 3 variables and 2 variables. When we have 3 variables and we have a solution which is sorry.
3 variables.
Yes. If we have a solution that gives us a unique solution, sorry, for a 2 variable, if it is a unique solution, and for the linear equation with 3 variable, will it give a
so you're saying 2 equations?
Yes.
Unique solution here. Okay.
Yes.
You're asking
will it differ if we have 3 variables? Will it have infinitely many solutions for the same thing?
This is what we saw, no, in GeoGebra. The same thing.
That's my doubt.
Were plotting, because this is a plane.
Yes.
And this is a plane in R3. So when 2 planes intersect, you will have a line of intersection. Infinitely many.
Okay. For the same thing, for two variables, we'll have a unique solution.
Yeah.
Okay, that was my doubt, ma'am. Thank you.
Oh. Okay, so shall we
Excuse me, ma'am.
close? Yeah.
Okay, ma'am.
Ma'am,
Thank you.
one small question, like not related
Yes.
directly to this. Can you show once how to like put equations in GeoGebra? I get confused sometimes.
I just enter it. I'm not very good at it. I just enter it here, just like that.
In the algebra section. So for plane, we just directly put in x plus 2.
Yeah, that's it.
Ma'am, there's a small request I have.
Yeah.
On Fridays, our live session, is almost, adjacent to the statistics session. So one is at 6 to 8 and the other is 8 to 10. So they usually, and it is natural that we overshoot the time. So what happens is we have to see one of the subjects on YouTube if we're having both maths 2 and statistics 2. So it becomes a little difficult.
This timetable has been made in such a way that it can accommodate a person taking maximum number of courses. A person taking maximum number of courses can attend all the sessions. That's how the timetable is made.
We can, but then what happens is, and it's natural, we always overshoot by at least 15 to 20 minutes in every session. So that means once our maths 2
That's
session...
initially. Actually, in maths 2, sessions go on for 3-4 hours. Like, that's very natural.
If this is an every week routine on a Friday, I mean, if it's just a revision class, we can manage. But if this is a routine every week, then we'll be missing out on one of the two subjects, at least not be able to attend it live. So there is a little difficulty then. If just half an hour gap can be put in.
I'll inform this, I'll put forth this concern, but I don't think...
Ma'am, actually what it
if
happens
you could just
is,
put it across,
like it's
definitely.
overlapped, right? If it is getting extended, so it's getting overlapped with the statistics one. So we have to leave in the middle and join there or something like that. So
and sometimes a very important topic is being discussed in the later part of the session of maths 2. So we don't want to even leave it. And when you
but we have
enter
to sometimes,
and in statistics too, maybe some announcements are being made or some clarification is required at your end, then that cannot happen.
So at least if it is like it's from 6 to 8, if it starts from 5 also, then we can manage.
No 5. Sorry, no 5, please.
5 or 5:30 or even in the morning.
No. After 6:30
most sessions are starting before 5 because before 6, because keeping students who are actually attending colleges.
No, you can suggest statistics to postpone to starting from 8:30, no? What is there in that? Or 9 o'clock?
That can also happen. Like anything that...
No, don't prepone anything. 6 o'clock itself is very tight.
Concerned will take care of that. I was just telling that it shouldn't like overlap because generally
then
half an hour
get
gap
extended.
8:30.
I'll put forth the concern. We'll let them to decide.
Yes.
But don't prepone anything.
Madam, kindly.
Yeah.
They're all working working people are there in this batch as well as all the other colleagues also object.
Yeah.
A terrible time. We'll have a terrible.
6 o'clock itself is very tight and it's very. We are
more often than not, our counterparts are in the West, so we have to stay till 6 o'clock at the very minimum, and we are having to balance these things. So it'd be great if we keep it.
I don't think it will be preponed for sure.
Okay.
Means 100% it won't be preponed.
Set it at
But about postponement, I'm not sure.
12 o'clock is also fine, but before 6 o'clock.
Yes. Morning 5 o'clock also fine, but
fine.
Don't prepone anything now. Itself we are missing many things. And,
Hello, ma'am.
Yeah.
Ma'am, my question is slightly different from the course. Yes. Is there any support for provide a laptop or something that for economical weaker section students?
Can you mail this to the support team because we don't have any info about it. They'll be able to help you better.
Yes, sir. I mailed the support team, but they said there is nothing such support. But beginners are in the past Q&A session said that there is a CSR team that this team will provide us like economical weaker student laptop like things.
Oh, but we have no information about it. So
Okay,
whatever
okay.
the support team tells, yeah, that's what.
Okay.
Okay, then I guess we'll close the session. So on Tuesday, the next session will happen.
Okay, thank you.
Yeah, thank you.
Thank you.
Thank you, ma'am.
Thank you.
Ma'am. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you.
Leave.